So we move on to a fundamental theorem of calculus. It's one of the most important theorems in calculus. Mostly it deals with integrals. And the key here is suppose f of x is a positive function and by positive function I mean f of x is greater than 0 for a less than x less than equal to b on some interval. Then we know f of integral a to b f of x dx is the area under the curve. So, for instance, if I have So if I pick A and B, then the area under the curve, which would be all of this, all of it here, would form the integral a to b f of x dx. That's great. Now I'm going to copy this. So the same function, but what I'm going to do now, I'm going to pick an arbitrary line between A and B, and I'm going to call it T. So imagine if I move this T between A and B, then the area will change with respect to T. Now that is a given, it should be obvious, and I'll draw a couple of images to demonstrate this. So if T is right over there, then the area would be all of that. And if I move that T a bit, and let's say I drew it over here, then the area under the curve would be that pi. So we know that the integral is a real number. It would also imply, because it is the area under the curve, we also know that the area I have here and the area I have there A1 and A2 are also real numbers. The only difference here is that the value changes with respect to t. Perhaps I could use a different letter to avoid confusion. I'm going to call that some arbitrary value x. So as I move that x, the area is going to change. So if x is x1 there, then this area would simply be integral a to x1 f of some t dt. That t is what we call a dummy variable. So x is x1. If I pick x is equal to x2, then this area, a2, would be integral a to x2 f of t dt. And from the figures, you can see that the area A1 is greater than A2. You can see that clearly. A1 is bigger than A2. So what does the first fundamental theorem of calculus state? Now, if I keep on moving this line, the red line and the purple line, back and forth, I'm going to get different values for the area. So the fundamental theorem of calculus, I would say this is rule 1, states that g of x is equal to integral a to x, the dummy variable t, dt. And g of x is a continuous function. As an example, I can relate this to what I used up there. So here, if I plug in g of x1, that would equal to the area A1, and g of x2 would equal to the area A2. So I could pick any x, and I could come up with a continuous function that represents the area under the curve. So that is the first fundamental theorem of calculus. You could call it FTC 1. Now, there is a close relationship between this area and the derivative, and which is one of the reasons we call it the antiderivative. So what is an antiderivative and how can we visualize this? suppose we have a function and let's say I have a curve of that sort between A and B, and I'm going to pick two lines and those two lines are x and x plus h, and of course I would end up having f of x and f of x plus h. And that right there is an area, which we know. And the distance between x and x plus h is simply h. And that point right there is f of x. And that point right there is f of x plus h. And keep in mind, we can find that area either using the left endpoint or the right endpoint. So, using the definition from FTC1, Fundamental of Theorem of Calculus 1, I could write g of x plus h as integral a to x plus h f of t dt. T is just a dummy variable. And g of x as a to x f of t dt, that is also a dummy variable. Now, if I subtract the two, g of x plus h minus g of x, that would simply be integral a to x plus h f of t dt minus integral a to x f of t dt. Now, I could also write this using one of the properties of definite integrals. The area all the way up to x plus h is simply, perhaps I should copy this. So I can rewrite the area up to x plus h as this. So the area from a to x and the area from x to x plus h. So if I call this A1 and if I call that A2, the area from A to x plus h is simply A1 plus A2. And then I have the third term minus integral a to x f of t dt. So what is A1? A1 is integral a to x f of t dt. A2 is integral x to x plus h f of t dt minus integral a to x f of t dt. The first and the last terms would get cancelled. I'd simply have integral x to x plus h f of t dt. Now that is simply the area under the curve A2, because we are simply looking from x all the way up to x plus h. So that is simply A2. But if we use the rectangle, approximation rectangle, that is simply equal to h times f of x. I'm using the left endpoint. So what we have shown is g of x plus h minus g of x is approximately equal to h times f of x. This would imply g of x plus h minus g of x divided by h would be approximately equal to f of x, which would mean limit h approaches 0, g of x plus h minus g of x divided by h would be approximately equal to f of x, but in limit it would simply be equal to f of x. But the left-hand side, by definition of derivative, the left-hand side is simply the derivative of g of x. So g prime of x would equal to f of x. Hence, g of x is called the antiderivative. So now you could see the relationship between the antiderivative and the derivative, the integral. So another way to write it, we know that g of x integral a to x f of t dt, d over dx of g of x is simply g prime of x, would equal d over dx of integral a to x f of t dt, and that would equal f of x from our previous argument right over here. So we could infer it this way also, and this is what we call the Leibniz notation. But all we are trying to say is the derivative of g of x, which is the integral, would equal to the function f of x, and they are called the antiderivatives. So here we have an example. G of x is equal to integral 0 to f of t. The function is defined between 0 and 6. So x is in 0 all the way up to 6. And we want to evaluate g of x for x is equal to 0, 1, 2, 3, 4, 5, and 6. So g of 0 would be integral 0 to 0 f of t dt. What is the area from 0 to 0? Nothing, so that will be 0. G of 1 integral 0 to 1 f of t dt would equal that area right there. So that is the area of a right angle triangle, base 1, height 1. So we have 1/2. Next, g of 2 is integral 0 to 2 f of t dt, which I could write it as integral 0 to 1 f of t dt plus integral 1 to 2 f of t dt. So that would mean I have to take that area 1 to 2 and add it to the previous value. So I have 1/2 plus the other area is also a right angle triangle, so 1/2 multiplied by -1 times 1. In this case, it's going in the opposite direction. So we have 1/2 minus half, the net area is 0. Now, g3 is integral 0 to 3 f of t dt, which I could write it as integral 0 to 1 f of t dt plus 1 to 2 f of t dt plus integral 2 to 3 f of t dt. And that would equal to that area. So what we have, that is the that is the area up to 2, that is the area up to 1. And now we have to find the area all the way up to 3. So what we have is 0 to 1 is 1. 1 to 2 is -1. And we are going in the reverse direction again. So 1/2 minus 1 and 1. And that would equal to -1/2. Now we have to move on to g of 4. So we have to find that area and add it to all the previous values. So g of 4 is simply g of 0 plus g of 1 plus g of 2 plus g of 3 plus integral 3 to 4 f of t dt. Or, oh, sorry, I didn't mean to write it that way. So that simply means g of 3 plus integral 3 to 4 f of t dt. So -1/2 and 3 to 4 f of t dt would be 1 times 1 divided by 2, which gives us 0. Now we have 4 to 5 to be added with the previous values, so that we would get integral 0 to 5 f of t dt. So we have to add that area to the previous values. So g of 4 plus integral 4 to 5 f of t dt. So g of 4 would simply be 0 that we had, and 4 to 5 has a triangle over there and a square. So the area of the triangle is 1/2 base times height, plus the square is 1 times 1, so we have 3/2. Now we can move on to finding g of 6, which is simply g of 5 and 5 to 6 f of t dt. And that would equal to 5 to 6, okay? So 5 to 6, we have that square. Another square. And a right angle triangle. So area of the square is 1 plus 1. The area of the triangle is 1/2, 1/2, plus g of 5, which is 3/2. So we get 2, 3, 4. So the answer is 4. And lastly, we want to estimate the value of g of 7 from the picture. G of 7 is simply g of 6 plus integral 6 to 7 f of t dt. We already know g of 6 is 4, and we have to find that area. And what we have is 4, but if you look at the area from 6 to 7, we don't have a straight line. Rather, it is a curved line, and the area of that is going to be less than. So, of course, we have a triangle, kind of a triangle, kind of a square, and kind of another square, because there is a curve here. It's not a straight line. So whatever value we find for 6 to 7 f of t dt has to be less than the area of the square, area of the other square, and the area of the triangle, which is approximately 1/2 times 1/2 times 1. So the base length is probably about 1/2. So that's my assumption. So integral 6 to 7 has to be 1 plus 1 plus 1/4, and integral 6 to 7 has to be f of t less than 2 plus 1/4, that is 9 over 4. So that would be 9 over 4. So I can say that g of 7 is approximately equal to 25 over 4, or I could say that g of 7 is going to be greater than g of 6 for sure, which is 4, less than 25 over 4. Because I'm trying to estimate the value, and I see that the estimate is going to lie between 4 and 25 over 4. So here we want to find the derivative of the function using fundamental theorem of calculus 1. The fundamental theorem of calculus, part 1, states g of x. If g of x is defined as 1 to x, ln of 1 plus t squared dt, then f of t dt, then g prime of x must equal f of x. That's what the theorem states. Therefore, the derivative of g of x is simply ln of 1 plus x squared. So here we have a function in terms of u. T here is the dummy variable. So what does the fundamental theorem of calculus state? FTC1 states h of u equals integral 0 to u f of t dt implies h prime of u is simply f of u. Therefore, the derivative of h of u is h prime of u, which would be square root of u divided by u plus 1. So it's very straightforward using the fundamental theorem of calculus 1. So this one is a bit tricky because we don't have simply x. Rather, we have x plus 2. So we can't directly apply this. So what we have to do is use a substitution. So let u equals 3x plus 2. Then what we have is du over dx would be equal to 3. Now, what is the derivative of y? The derivative of y is y prime, and that is dy over dx. Since y is a function of u and not x by itself, I could write this as dy over du multiplied by du over dx. That's simply the chain rule. So in terms of u, y would be integral 1 to u t over 1 plus t cubed dt. I could even call it y of u so that you can relate it to the previous problem on how we replace the u. So this would mean by FTC1, y prime of u would be equal to u over 1 plus u cubed. Now we want to find y prime of x as a function of x. This is what we need to find. And what we found here is that. So y prime of x would be u over 1 plus u cubed multiplied by du over dx, which is 3. This would mean y prime, we have to replace u by the substitution. So we have 3x plus 2 divided by 1 plus 3x plus 2 cubed multiplied by 3. So anytime you have something other than just x, you've got to use this process to apply the fundamental theorem of calculus properly. So here is a similar problem. What I'm going to do, it says x4, that should actually be x raised 4. So y here is a function of theta. So, not theta, it's a function of x raised 4. So first, I'm going to let u equals x raised 4, which would mean the derivative of u with respect to x is 4x cubed. Y of x is integral 0 to x raised 4 cosine squared theta d theta. Note that theta is a dummy variable, just like the t we had earlier. We want to transform this to y as a function of u. So we have 0 to u cosine squared theta d theta. Now we know the derivative of y as a function of u is simply cosine squared u. That is by fundamental theorem of calculus 1. But we want to find the derivative of y as a function of x. In other words, y prime. In other words, dy over dx. But I could write dy over dx as dy over du multiplied by du over dx. I know dy over du, which is right over here. And that is cosine squared u. I also know du over dx from earlier, which is 4x cubed. So y prime is cosine squared x raised 4 multiplied by 4x cubed. Fundamental theorem of calculus 2. Or part 2, I should say, not calculus 2 as the course. So from FTC1, we know g of x is integral a to x f of t dt. Now, I mentioned antiderivatives earlier. but this is more formal. So we also know g prime of x would give us f of x. This is from FTC1 also. Now that g prime of x, uppercase f of x, be equal to g prime of x plus some constant, g of x plus some constant c. Now the reason being is when we take the antiderivative, we do not know the constant that gets added. In other words, we can get an antiderivative So both of these lines would have the same antiderivative. So f1 of x, f2 of x. So antiderivative f1 of x and f2 of x are one and the same, but both of them have the same underlying function. Let's just say y equals x plus 1, y equals x minus 1. But what is the antiderivative here? G of x is simply y is x. So the underlying function is simply g of x. But it could either result in minus 1 or plus 1 as the constant, which is why we throw in the constant for the integration part. This is what we call the constant of integration. So what does FTC2 state? Integral a to b f of x dx is simply equal to f of b minus f of a, where f of x is the antiderivative of lowercase f of x. In other words, if I took the derivative of f of x, I should get lowercase f of x. Now, the constant doesn't matter when we evaluate a definite integral, because the c's would just get cancelled. The constant matters when we have a function, in which case we have to specify the constant. So, here is a problem where we want to evaluate the integral of this function. So our objective is to find f of x so that f prime of x equals x raised 100. So you have to come up with a number so that the derivative of that would equal, come up with a function so that its derivative is x raised 100. So let's just say f of x is x raised 100 over 100. Then f prime of x is 100 times x raised 100 minus 1, which is now x raised 99 over 100. Those two would get cancelled. I get x raised 99. But this isn't correct because what we want is x raised 100. So let's say we have x raised 101 divided by 101. So f prime of x would be 101, x raised 101 minus 1 over 101, which gives us x raised 100. So the antiderivative of f of x equals x raised 100 is uppercase f of x, which is equal to x raised 101 over 101. Now what does the second fundamental theorem of calculus state? So by FTC2, integral a to b f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. So we have a to b minus 1, b to b 1. So 1 raised 101 divided by 101 minus 1 raised 101 over 101. And we can say that the power is odd. So if you have minus 1 raised to odd power, you get minus 1. So minus of minus 1 raised over 101. So the answer is 2 over 101. So now we have a function, f of v is 1 minus 8v cubed plus 16v raised 7. We want to find its antiderivative. So let's look at it piece by piece. What should the antiderivative of f of v be? Well, I want to differentiate something so that I get 1. What should I differentiate? If I took the derivative of v with respect to v, I would get 1. I want to take the derivative of something so that I get v cubed. V raised 4 over 4. I want to take the derivative of something, so I get v raised 7. V raised 8 over 8. Let's verify. Is f prime of v equal to f of v? Well, f prime of v, derivative of v is 1. Derivative of v raised 4 is 4v cubed divided by 4. Derivative of v raised 8 is 8v raised 7 divided by 8. 8's go away, 4's go away. We have 1 minus 8v cubed plus 16v raised 7. That is f of v, which we had here. So we have the right antiderivative. This process might seem like trial and error, which of course it is, but later on we have easier ways to find this. Now, we want to find the value of the integral 0 to 1, 1 minus 8v cubed plus 16v raised 7 dv is simply f of 1 minus f of 0. So when I plug in the upper limit, I have 1 minus 8, 1 raised 4 over 4, plus 16, 1 raised 8 over 8. Lower limit, I have 1, 0, minus 8 times 0 raised 4 over 4, plus 16, 0 raised 8 over 8. So we simply have 1 minus 2 plus 2 minus 0, which would give us an answer of 1. Here is another problem where we have to find the integral. Of course, we can find it using techniques that you'll learn later on at the end of this course or in Calculus 2. But without that knowledge, how do we find the antiderivative? The first thing to do is to recognize what f of t is. F of t is 4 minus t multiplied by square root of t. So before we move on, I'm going to rewrite f of t as 4 minus t, t raised 1 over 2, which is 4 t raised 1 over 2 minus t raised 3 over 2. So I want to find the derivative of something so that I end up getting f of t. In other words, what is the antiderivative? So 4 remains as is. So we know when we take the derivative, we subtract 1 and we multiply by the power. Here, I'm just going to add 1 and divide by that so that I'll go in reverse. Do the same. Add 1 and divide by that, which would give us 4 t raised 3 over 2 over 3 over 2, t raised 5 over 2 over 5 over 2. That should be f of t. The next question to ask is the derivative of this function equal to f of t. So the derivative of the function is 4, 3 over 2, t raised 3 over 2 minus 1, divided by 3 over 2, minus 5 over 2, t raised 5 over 2 minus 1, divided by 5 over 2. Those two would go away, and we have 4 raised 3 over 2 minus 1 is 1 over 2, minus 5 over 2 minus 1 is 3 over 2. Is that f of t? Yes, it is. So that's what we have here. So it matches up. So we have the correct antiderivative. So integral 0 to 4, 4 minus t square root of t dt would simply be equal to uppercase f evaluated at 4 minus uppercase f evaluated at 0. So we have those values: 4 raised 3 over 2 over 3 over 2 minus 4 raised 5 over 2 over 5 over 2. Lower limit would simply give us 0 raised 3 over 2 over 3 over 2 minus 0 raised 5 over 2 over 5 over 2. So integral 0 to 4, 4 minus t square root of t dt would be 4 4 raised 3 over 2, I could write it as 4 raised 1 over 2 raised 3. Flip and multiply, 2 over 3. 4 raised 1 over 2 raised 5. Flip and multiply, 2 over 5. The second term would be 0. So 4 times 2 cubed times 2 over 3 minus 2 raised 5 times 2 over 5, which would give us 16 over 3 minus 64 over 5, 80 over 15 minus 192 over 15, which would give us negative 112 over 15 minus 448 over 15. That is the net area. So in practical situations, we need to have a positive value. So here is another example. We're going to do this just by using the fundamental theorem of calculus. So what we start with is the function f of u, which is right here. F of u is 3u minus 2 multiplied by u plus 1, which would give us 3u squared plus 3u minus 2u minus 2, 3u squared plus u minus 2. Now we have to find the antiderivative. F of u. In other words, if we differentiate uppercase f of u, I need to get lowercase f of u. So let's see, 3. With derivatives, we subtract 1, so I'm going to add 1 and divide by 3. Add 1, 1 plus 1 is 2, divide by 2. If you took the derivative of something, you need to get 2. And we know if I took the derivative of 2, it is 0. But if I took the derivative of 2u, I would get 2. So that is the correct derivative. So let's see if we get what we had before. So is f prime of u equal to f of u? Always verify. So f prime of u is 3 times 3u squared over 3 plus 2u over 2 minus 2. The 3's go away, 2's go away. I end up getting 2u squared plus u minus 2, which is f of u. So works out. We have the correct antiderivative. So the integral minus 1 to 2, 3u minus 2 times u plus 1 du is simply uppercase f evaluated at 2 minus uppercase f evaluated at negative 1. So you have 3 times 2 squared plus 2 minus 2 minus 3 times minus 1 squared minus 1 minus 2. So 4 times 3 is 12. 2 minus 2 is 0. Minus 3 minus 3, which is 0. So the answer is 12. So here we have a function that's trigonometric, exponential. So first step is to find the antiderivative. So What function would give us sine x when we differentiate it? Well, if you differentiate cosine x, we get minus sine x. So recall, derivative of cosine x is minus sine x, which would imply derivative of minus cosine x has to be minus of minus sine x, which is sine x. So this has to be minus cosine x. What function would give us exponential when we take a derivative? Derivative of e raised x is e raised x. So this has to be e raised x. So my antiderivative is 2 cosine x minus e raised x. Some of you might recognize that we have the correct antiderivative, but let's verify. Is f prime of x equal to lowercase f of x? Take the derivative of f prime of x. Minus 2, derivative of cosine x is minus sine x, minus derivative of e raised x is e raised x. We get 2 sine x minus e raised x. Does that match to f of x? It does. That's what we started with, 2 sine x minus e raised x. So we have the correct antiderivative. So integral 0 to 3, 2 sine x minus e raised x is simply f of 3, uppercase f of 3, minus uppercase f of 0. So uppercase f of 3 is minus 2 cosine 3 minus e raised 3 minus 2 cosine 0 with a minus e raised 0. So we get minus 2 cosine 3 minus e cubed minus cosine 0 is 1 minus e raised 0 is 1. So minus 2 cosine 3 minus e cubed minus of minus 3. So the answer is 3 minus 2 cosine 3 minus e cubed. You can use the calculator to get a decimal value as an answer. So now we have a piecewise function where between negative 2 and 0 we have 2, and 0 and 2 we have 4 minus x squared. So we have to find the derivative, the integral. So integral minus 2 to 2 f of x dx. Since we have two pieces, I'm going to split right at the piece, which is 0. And we should always note if this function is continuous. You can see that at x is equal to 0, it is not continuous. So minus 2 to 0 f of x dx plus integral 0 to 2 f of x dx. One of the properties of integrals. So minus 2 to 0 2 dx, integral 0 to 2, 4 minus x squared dx. Let's graph this. So negative 2 up to 0, what we have, including 2, including 0, when I plug in 0, the second piece, I end up getting an open dot at 4. And when I plug in 2, I end up getting 0, and it's a parabola, so it would probably go, oh, no. Something like that. So one has a closed dot, the other has an open dot. So what do we do in this problem? So the key to note here is, at the end of the day, we're simply trying to find the area over there and the area over here. So that jump doesn't matter because we're just going to integrate it piece by piece and add the areas. So the first integral is integral minus 2 to 0, 2 dx. So what is the antiderivative? The function here is 2. So what function would give us 2 when we take the derivative? It has to be 2x, because f prime of x would be 2. So integral minus 2 to 0, 2 dx would simply be equal to f of 0 minus f of minus 2. So 2 times 0 minus 2 times minus 2, which would give us 4. Integral 0 to 2, 4 minus x squared dx. Now, what should the antiderivative be? You have to differentiate something to get 4, so it has to be 4x. If I differentiate 4x, I am going to get 4. If I differentiate x cubed over 3, the derivative is 3x squared over 3. You will end up getting x squared. So that would be our antiderivative. This would mean integral 0 to 2, 4 minus x squared dx would be 4 times 2 minus 2 cubed over 3 minus 4 times 0 minus 0 cubed over 3. 8 minus 8 over 3 minus 0, which is 16 over 3. We're not done yet, so the total answer, minus 2 to 2 f of x dx, is the area from the first piece, which is 4, area from the second piece, 16 over 3, so we have 4 plus 16 over 3, which is 28 over 3. So we want to find the rough estimate of the area of the region that lies beneath the given curve, which is y is equal to x raised minus 4, and then we have to find the exact area. So It's x raised minus 4. When x is 1, it's going to be at 1. And it's 1 over 6 raised 4. That is going to be a small number. 1 over 36 over 36. It's close to 0. So it's going to be somewhere over there. Just drawing an approximate curve. And we want to find the area. Of course, we can either do a right-hand limit or a left-hand limit. We could use a certain number of rectangles. So what I'm going to do is I am going to, let's say, draw the lines here. I'm going to divide, made a mistake. Let's see if I can simply move this. Nope. Ah, that works. So that is at 1, not at 0. So I'm going to divide 1, 2, 3, 4, 5, 6. And I'm going to use rectangles. Now, I'm going to use the right endpoints. And that would be it. So those are my 6 rectangles, or 5 of them that I have. So I'm going to look at the width, which is simply 1. Have to evaluate those points. That would be 2 raised negative 4, 3 raised negative 4, 4 raised negative 4, 5 raised negative 4, 6 raised negative 4. I'm simply plugging in the values. So the area under the curve, integral x raised negative 4 dx from 1 to 6 would be sum I equals 1 to 5 f of xi times delta x. x1 is 2, x3, x2 is 3, x3 is 4, x4 is 5, and x6 is 6. So we end up getting 1 times 1 over 2 raised 4 plus 1 over 3 raised 4 plus 1 over 4 raised 4 plus 1 over 5 raised 4 plus 1 over 6 raised 4. We need a calculator. Let's see, 1 over 2 raised 4 is 1 over 16. So we have 0.0625. 1 over 3 raised 4 is 81. 0.0123. 1 over 256. 1 over 625, 1 over 1296, and we add all those values. .1305. So the area I found is 0.1305, and that of course is an approximate. Now I want to find the exact value. So the antiderivative of f of x equals x raised negative 4 is, let's see, it's minus 3 over minus 3. Let's take the derivative. Is f prime of x equal to f of x? Well, f prime of x is minus 3. X raised minus 3 minus 1 over minus 3. Those two would go away, have x raised minus 4. So we have the correct antiderivative. So integral 1 to 6 x raised minus 4 dx is simply f of uppercase f of 6 minus uppercase f of 1. F of 6 is simply 1 over 6 raised 4 minus lowercase is 1 over 1. 1 over 6 raised 4 and minus 1 have negative 0.9999. But I forgot to divide by, I'm sorry, plugging it in the wrong antiderivative. So f of 6 minus f of 1, which is 6 raised negative 3 over negative 3, minus 1 raised negative 3 over negative 3. So we have 6 raised negative 3 divided by 3 with a negative. So we have minus 0.0015 plus 1 over 3. And the correct answer is 0.3318. So our estimate is slightly off, and we know from previous topics that this is going to be an underestimate, because we could see that we are missing out that area over there, that over there, that over there, that over there, and that. So that is the amount that the approximation is missing, which is why our value 0.1305 is lower than the exact value. So this is an underestimate. And that's the exact value. So we have y is equal to sine x, and we've got to estimate the area. Then we have to find the exact area. So let's go ahead and graph it first. Now sine between 0 and pi has that shape. If I could get that right. And that would be at pi over 2. And that value is 1. Let me divide this delta x pi minus 0 over 6. So 0 to pi over 6. Pi over 3. 3 pi over 6. 4 pi over 6 is 2 pi over 3. 5 pi over 6. And each of those values we can evaluate it using the calculator. So I'm going to go to the left. And those would be my values. Oh. So, right there. There. Right there. Okay. So those are the rectangles that I have, and we want to find the areas. So delta x is pi over 6, and the area 0 to pi sine x dx would be sum I equals 1 to 5 f of xi delta x. So x1 is pi over 6, x2 is pi over 3, x3 is pi over 2, x4 is 2 pi over 3, x5 is 5 pi over 6, and delta x is pi over 6, so I'm going to pull that out of the sum. So y is sine x, and I am going to table set so that I could do this really fast. The increment value is pi over 6, and second table. Sine 0 is 0, that we don't want that. We simply want sine pi over 6 plus sine pi over 3 plus sine pi over 2 plus sine 2 pi over 3 plus sine 5 pi over 6, which would give us pi over 6, 0.5 plus 0.866 plus 1, 0.866 plus 0.5, so 0.5, oops, so the net value is 0.9541, and that is the approximate area. Now what is the antiderivative? of sine x. You have some function, if you differentiate that, you have to get cosine x. So if I said the antiderivative, sine x, so if I said the antiderivative as cosine x minus cosine x, the derivative is minus of minus sine x, which is sine x, which is the function. So the antiderivative is f of x equals cosine x. So integral 0 to pi sine x dx would simply be equal to minus, well, f of pi minus f of 0, which is minus cosine pi minus cosine 0, minus of minus. Minus cosine pi is minus of minus 1, minus of minus 1, we end up getting 2. And you can see that this value is very close to our estimate. If you go back and look at it, we didn't miss a lot. Whatever we missed here in terms of the area, that's what I missed, and I missed some here, and I missed a bit over there, but I made up for it by overestimating there, and overestimating there. Which is why in this particular problem, I'm doing a little bit of overestimation, little bit of underestimation, things balance out, and my rough estimate is pretty much close to the actual value. So we want to find the derivative of this function, and what we're going to do is we're going to make use of the fundamental theorem of calculus. I think it's best if we did the fundamental theorem of calculus 1, because we don't want to find the antiderivative of u squared minus 1 divided by u squared plus 1. So how do we go about doing this? Well, if we want to use fundamental theorem of calculus 1, we need a constant lower limit. So why don't we start at 0? Now I can rewrite this integral as integral 0 to 3x u squared minus 1 over u squared plus 1 du minus integral 0 to 2x u squared minus 1 over u squared plus 1 du. That is going to give me the area between two x and 3x. So let me graph the function here. X squared minus 1 divided by x squared plus 1. I get something like that. So an arbitrary 3x and arbitrary 2x. It's not so obvious here in that graph, so I'll just draw something like that. So suppose I have the area below 3x. And then I have the area below 2x. And if I subtract them, so area below 3x would be all of those. That is the area below 3x. And area below 2x is that part. If I subtract them, I'm going to end up getting this part. And that would be integral 2x to 3x u squared minus 1 over u squared plus 1 du. So now, I'm going to split g of x as integral 0 to 3x u squared minus 1 over u squared plus 1 du minus integral 0 to 2x u squared minus 1 over u squared plus 1 du. We have to make two different substitutions, so I'm going to call that u1, and I'll call that, u2. And our function y is that. So y of u is u squared minus 1 divided by u squared plus 1. And our limits are 3x and 2x. And we want to find the derivative in terms of x. So dy over dx, I could write it as dy over du1 times du1 divided by dx. That's for the first integral. Dy over du1 would simply be equal to u1 squared minus 1 divided by u1 squared plus 1. That's using fundamental theorem of calculus 1. Because I simply have y of u1 to be integral 0 to u1 u squared minus 1 over u squared plus 1 times du. And to take the derivative, I simply plug in u1. Times du over dx is simply 3. Over here, y of u is u squared minus 1 over u squared plus 1. dy over dx is simply dy over du2 times du2 over dx. U is just a dummy variable, so we don't have to worry about that. So that would equal to u2 squared minus 1 divided by u2 squared plus 1 multiplied by the derivative of u2 with respect to x is 2. Now plug in the substitutions. We have 3x squared minus 1 over 3x squared plus 1 multiplied by 3. 2 times 2x squared minus 1 divided by 2 times 2x squared plus 1. 2 shouldn't be there. So 3 times 9x squared minus 1 divided by 9x squared plus 1 plus 2 times 4x squared minus 1 divided by 4x squared plus 1. Think we can simplify this. So 3 times 9x squared minus 1 times 4x squared plus 1 over 9x squared plus 1 times 4x squared plus 1. 2 times 4x squared minus 1 times 9x squared minus 1 divided by, plus 1, divided by 9x squared plus 1 times 4x squared plus 1. Distribute and simplify. 108x squared, x raised 4 plus 27x squared minus 12x squared minus 3 plus 36, 72x raised 4 plus 8x squared minus 18x squared minus 2. 9x squared plus 1 times 4x squared plus 1. Don't know if it's going to simplify much. 180x raised 4. 27, 35, and 30. That'll be 5x squared minus 5 divided by 9x squared plus 1 times 4x squared plus 1. I guess I could pull 5 out. 36x raised 4 plus 5 minus 1, 5x squared. Could we factor the numerator? Something tells me we can. Let's just do 9x squared minus 1 times 4x squared plus 1. That would equal to 36x raised 4 plus 9x squared minus 4x squared plus 1. Which is the numerator. So I could rewrite it as 9x squared minus 1 times 4x squared plus 1 divided by 9x squared plus 1 times 4x squared plus 1. Those two would go away. I'd simply have 5 times 9x squared minus 1 over 9x squared plus 1. Okay. Here we have a similar problem. We have to make two different substitutions here. We have a sine x and we have a cosine x. This is not as straightforward as the previous one because we have sine and cosine. We have sine x and cosine x here, but let me just go back to this problem. I think might have messed up on a sign. It doesn't sit right with me. Oh, no. That's minus. We had a minus. So minus, that's going to change everything. Minus. So that would become minus 3 minus 72x raised 4 minus 8x squared plus 18x squared plus 2. Which would give us 108 minus 72, that is 36 x raised 4. 27, 18 minus 30, 5x squared minus 1. Minus 20, 27, minus 27, 25x squared. Plus 10, 37. It's 25x squared. We could have left it at the first step, but I'm just trying to simplify here. I don't think we can simplify this further. Of course, we can try factoring and such, but I'm not going to do that because it's not going to be nice. Plus 18 minus 8x squared. Okay. Okay, we'll just leave it at that. So here we have the function f of x here, and we can split this integral as cosine x to 0 integral 0 to sine x. Since we have to have 0, I can flip the limits of integration, but when I do that, I have to change the sign. So don't forget that. I'll write a remark. So now we have u1, u1, u2, same thing like we did in the previous problem. So y of v is ln of 1 plus 2v. Well, dy over dx, I could write it as dy over du1 times du1 over dx. So the derivative of y with respect to u1 is simply ln of 1 plus 2 u1 Derivative of u1 with respect to x is minus sine x. There is a minus in the front. Over here, dy over dx is simply dy over du2, du2 over dx. Dy over du2 is ln of 1 plus 2 sine, 2u2, and derivative of u2 with respect to x is cosine x because u2 is sine x. Replace the substitution, so we have minus ln of 1 plus 2 cosine x multiplied by negative sine x. Here ln of 1 plus 2 sine x multiplied by cosine x. And minus times minus is plus. So the solution is y prime is simply sine x times ln of 1 plus 2 cosine x plus cosine x times ln of 1 plus 2 sine x. And that would be it based on the fundamental theorem of calculus part 1. Though you shouldn't do fundamental theorem of calculus part 2 in a problem like this, easier way to recognize it is the limits. If the limits are functions such as sine x and cosine x, we simply use fundamental theorem of calculus part 1.